Hi everyone, this is week 10 and this week we are going to cover fundamental theorem of calculus, which is a very useful theorem to compute derivatives of integrals. This is a very useful shortcut, and then we will talk about substitution technique a bit, and then to compute indefinite integrals we can use substitutions, and next we will look at definite integrals and how to use them to compute areas between curves. This is the summary of this week. Okay, let's start with the first group. The first group is about taking integrals. Now, finally, we are ready to compute integration by using the integration rules. For this part, I can remind you first, fundamental theorem of calculus part 2. Okay, recall. Then we will mention part 1, but this first group is about fundamental theorem of calculus part 1. Part 2. Okay, integral of the derivative of a function. You see, integration and derivation are inverse operations. Let's write this down. Integration and derivation. These are inverse operations. Don't forget this, okay? Inverse operations. So here, what do you see? We first take the derivative and then we are trying to take the integral. That's why they will kind of neutralize each other, okay? So you can expect the result just depending on the function. That it does make sense, right? Because these two are inverse operation, they will neutralize each other. But if we put some boundaries here, let's deal with this definite integral, then the result will just depend on f of x, but evaluated at this upper level bounds, okay? From a to b. What does this notation mean? It is f evaluated at b, f evaluated at a, and you will take the difference. So to compute the integral, to guess this result of the integral, you can think in a way that what should be a function whose derivative is this one, okay? So you can try to think in this way to find out the, okay, let me tell you from the example. Okay, let's start with 32, this one. 2 to 4, x to the power pi minus 1 dx, okay? So to guess this result, so I want to guess f of x now. Then what you should think? Tell me a function whose derivative is this one, okay? Tell me a function whose derivative is x to the power pi minus 1. So do you remember antiderivatives that we covered like last week? So x to the power n, I can write it as an integration rule. Now we talked about this rule last week as antiderivatives, but now I will put this integration notation. So tell me a function whose derivative is x to the power n, the power function. Of course, you need to add 1 to the power because while taking the derivative, the power is decreased by 1. And to get rid of the extra coefficient, you need to divide by n plus 1. Since this is an indefinite integral, you need to put this arbitrary constant c here, okay? And this rule applies only for n different than minus 1, because if you choose n equals minus 1, this is not defined. For n equals minus 1, there is another famous integration rule. We will cover it soon next week. Okay, so by using this integration rule for power functions now, you can easily tell me the result. What is the power here? It is pi minus 1, right? So you add 1 to the power, you divide by the same power. This is a definite integral. That's why you need to evaluate this result at this upper level boundaries, okay? So insert 4 for x, then insert 2 for x. Then you will take the difference to the power pi divided by, you will take the difference, okay? This is how you evaluate definite integrals. Now let's try 26. 26 is given as 0 to pi over 3 cosine x secant x to the power 2 dx. Okay, before starting the evaluation of integrations, we need to compute this square first, right? So it is cosine square x plus 2 times cosine x secant x plus secant square x dx. Okay. Now, we can use the famous half angle formula here. This is cosine square x. And whenever you see cosine square or sine square, you can insert this famous half angle formula, 1 plus cosine 2x over 2. And here what we have is secant means 1 over cosine x. Then this cosine x will simplify this 1 over cosine. And what do we have now? We have integral of 1 plus cosine 2x over 2 plus we have just 2 here, right? After simplifying, we have just 2. And then for the last part, okay, let's separate the expressions like this. You can just distribute integral sign to all the sums and differences. And the last integral looks like this. All of them is from 0 to pi over 3, okay? Like that. And here for the first one, you can take this 1/2 coefficient to the outside from the integral to the front like that. So let's start taking the integrals now. 1 over 2 is a coefficient there. Integral of 1. Tell me a function whose derivative is 1. It is, of course, just x. Tell me a function whose derivative is cosine 2x. So it should be sine 2x. To get rid of an extra coefficient coming from the derivative, you need to put this 1/2 here. Okay, this is the integration of the first expression. You need to evaluate it from 0 to pi over 3. Integral of 2 is just 2x. And now tell me a function whose derivative is secant square x. Do you know such a function? There is a function whose derivative is secant square x. So that trigonometric function is tangent x. So the evaluations are all from 0 to pi over 3. Now, the integrations are evaluated. Now, all you need to do is to insert pi over 3 first. So pi over 3 sine 2 pi over 3 over 2 minus, then you will insert 0, okay? Minus 0 plus sine 0 over 2. This is what comes from the first expression. This notation means this. Insert pi over 3, then 0, take the difference, okay? And we keep doing the same for the next. So this is what? This is 2 times pi over 3 minus 2 times 0. And now the last expression is tangent pi over 3 minus tangent 0. Okay, if you evaluate all those things there, the result turns out to be as this number. Okay, the result of the definite integral should be a real number because you are evaluating the resulting function at the upper boundary. At the lower boundary, you take the difference, so the result should be a real number. Okay, then let's move on with the next example, okay? Okay, let's try, for example, 34. This is the integral of pi to the power x minus 1 dx from minus 1 to 0. Remember, we evaluated this one, x to the power pi minus 1. This was easy because this was a power function, which has this simple rule of integration. Now we are changing the roles of x and pi. Pi to the power x minus 1. Be careful. The result of this integral is not evaluated like add 1 to the power, divide by the same power. No, this is terribly wrong. There is no such rule because this is not a power function. Power function. That's why you cannot apply this rule. What kind of function is this? In fact, it is an exponential function. Okay, it's a function of this form, 2 to the power x form. Do you remember, for example, 2 to the power x form? Do you remember how you take the integral of this thing? It was itself times ln 2. Then, can we guess the integration rule for that? So you should tell me now some function whose derivative is just 2 to the power x. Look at this rule and you can guess. Of course, in the derivative to obtain 2 to the power x, you should use this function. But if you just put this one, its derivative is not just 2 to the power x. There is this extra coefficient here. To get rid of that extra coefficient, you can put it to the denominator. So now, if you take the derivative of this, you will obtain 2 to the power x. That's why integral of 2 to the power x is this one. So this is the rule. This is a general rule for exponential functions. But if we use this spatial number instead of 2, let's use e. So tell me if you can use this general rule to find out the result. It is e to the power x divided by ln e. Ln e is 1, right? That's why we know the rule, integration rule for e to the power x is just itself, because tell me a function whose derivative is e to the power x, it's itself. Since these are all indefinite integrals, I am putting this extra arbitrary constant there. Okay, after discussing this part, let's solve our exercise. From -1 to 0, pi to the power x minus 1. So it should go like that. Instead of 2, we have pi here. So itself divided by ln pi, but this time it is definite, not indefinite. That's why I'm not putting a plus c, but I will evaluate the result for x equals -1 to x equals 0. Then the result becomes, insert 0 for x, so pi to the power -1 over pi. Next, insert -1 for x, pi to the power -2 ln pi. So this is your final result, okay? Any questions about this exercise? These boundaries are the boundaries for x. So I am inserting x equals 0, that next x equals -1. Any questions? So far, so good?
It's clear.
Okay, thank you for the reply. Now let's continue with this part. And this group of exercises are about fundamental theorem of calculus part 1. We exercised on fundamental theorem of calculus part 2. I forgot to write the name here, but this was fundamental theorem of calculus part 2, okay? Now, these are all covered in the recorded lecture videos. Now, in this group, we will use FTC part 1, fundamental theorem of calculus part 1, okay? We can analyze it into 3 different cases. So let me start with the simplest one. Okay, the simplest case. First, we are taking the integral ft dt. Then we want to take the, and this integral is from a to x, where a is an arbitrary real number. Then I will take the derivative of the result of this integral with respect to x, okay? Be careful. The result of this integral depends on x, right? Okay, after taking the integral, your function depends on t, okay. Apply integration rule, you will find the result as a function depending on t, but for t, you will insert first x, then a, you will take the difference. So the result of the full integral here will depend on x. depend on x, not t, because of this upper bound. And then it makes sense to take the derivative with respect to x again, right? So, fundamental theorem of calculus tells us the result. To find out the result, you don't need to take the integral, take this integral computation and then take the derivation back. It says that since integral and derivation are inverse operation, they will kind of neutralize each other. So what do you expect as the result? How do you feel? Integration and derivation are inverse operations. So they can neutralize each other so that the result will just be, but how do you feel about the result? If you neutralize integral and derivation, what is left? What remains here?
Just a function.
Yes, exactly. That's what fundamental theorem of calculus part 1 is. The result is just f of x. But be careful, I am not writing f of t here because you already inserted x and you take the derivative back. So everything is depending on x after this step. That's why, okay, they neutralize each other, but the result is just f of x, okay? This is what we call as fundamental theorem of calculus part 1. Now, I will discuss a more general case of this. These are all explained, but okay, let me discuss again. Let me recall for you. Okay, what if we have not just x, but some more general function here, u of x, a function depending on x. And what if we still want to apply FTC part 1? Still can be applied. Part 1. Okay. The rule goes like the similar. Of course, the result will just, we will just have f function as the result. Just f will remain. But this time, since it is more general, you should be careful. You will insert u of x again inside your function f. It's kind of you are evaluating f at x point, right? Again, similarly, you will evaluate f at whatever you see here. That's why I inserted ux function inside f function. According to chain rule, you have to multiply with the derivative of u function. So this is extra. In this more general case, the result is given like that. F evaluated at u of x times u prime of x. And there is this most general case where we have both functions at the lower bound and also at the upper bound. By the way, I should have written dt here, sorry. ft dt. This integral is derivated next. Then what happens? What we did here will be applied similarly, but there is also this part now. The lower bound also depends on x, right? So what you should do is you will do the same for ux. You evaluate f at ux, you multiply with the derivative of it. And then you will do the same for also the lower bound, okay? So f will be evaluated at the lower bound times derivative of it, and you will take the difference, okay? This is what you should, how you should find the result in this most general case. Okay, let's start applying those things now. Okay, start with 122. Our function y is given as from 2 to 7x squared. Function inside is given as square root of 2 plus cosine cube t dt. Okay, what we want to do, we want to compute the first derivative of the given function y. dy over dx we want to find out. So we want to take the derivative of the given integral. And this structure of the question totally fits to fundamental theorem of calculus part 1 for this case, right? You see we have u of x here. This is our u of x. What is f of t? F of t is given as this square root function. And, you know, this integral is, in fact, a very difficult integral to evaluate by hand. It is not an elementary integral. So, first of all, the first difficulty is this integral is not easy to evaluate. If we would evaluate it, then we should also take the derivative next, which will take too much time. Instead, you can use fundamental theorem of calculus part 1 to give the result in just a second. This is a very useful theorem, giving you the result in a second. This is very quick shortcut. It says that, look at your f function. This is our f. Inside of this f, we will put u of x, which is 7x squared, and then we will multiply with the derivative of u function. You see, I am applying fundamental theorem of calculus part 1, okay? So the result FTC part 1 goes like f of u of x times u prime of x. So f of u of x is like that. U is 7x squared. And then I will multiply with the derivative of u of x, which is derivative of 7x squared. So what is this? What is this now? It is, your function is given here, 2 plus square root of 2 plus cosine cube t. So instead of t, you will put this u of x function. It goes like 2 plus cosine cube. Instead of t, what we have u of x, 7x squared, okay? And then you will just multiply it with the derivative of u of x function, like this. Is that okay? So f function, which is given as square root function here, is evaluated at this upper bound. So that's why instead of t, I will insert 7x squared, and then this thing should be multiplied with the derivative of u function. So this is how you should apply fundamental theorem of calculus part 1. This is a very quick way of finding the result, and you can apply this for this type of questions where you have an integral and then you are trying to take the derivative of it, okay? Then you can apply FTC part 1 like that. Any questions? Okay, then let me show you one more from this group. So the y function is given now as this integral, ln x squared to 0 e to the power cosine t dt. And the question is, find the first derivative of y, not with respect to t, of course, because after, you see, if you have something depending on x at the boundaries, your function depends on x, so you can derive it with respect to x, okay? So dy over dx is d over dx of this y function, ln x squared to 0 e to the power cosine t dt. Okay. Did you notice something? To be able to apply fundamental theorem of calculus part 1, the constant should be at the bottom boundary and the x-dependent part should be at the upper boundary. So before applying fundamental theorem of calculus part 1, we need to interchange the boundaries. We need to change the places of the boundaries, right? Because constant should be at the lower boundary of always. Look at here. You see, the constant is always at the lower bound. So the structure has to be the same. That's why I am changing the places of the upper lower boundaries of this integral. Then, are they the same? Should I add something here? Since I changed the places of the boundaries, there is a property of definite integral saying that if you are changing the places of the upper lower bounds, you need to put an extra minus sign there. Okay, then that's the desired structure. And I can take this extra minus sign out. Let's take it out. Okay, now the question is exactly in the form to which I can apply fundamental theorem of calculus part 1. This is the desired structure. Constant is at the lower bound and x-dependent function is at the upper bound. And I will be applying fundamental theorem of calculus for this u of x. Okay, let's do that. FTC part 1. So this whole thing is the result of this whole thing. First integral, next derivation is given as, this is our f of t, right? F of t will be evaluated at this u of x here. So instead of t, I will be writing the given u of x, okay? Sorry, not just this, but there is also cosine, right? Okay, let me write it like that. Sorry. E to the power cosine of t, where instead of t, I should write this part ln x squared times ln x squared derivated. You see, this part, it comes from f of u of x, where u of x is ln x squared. And this part, this is our u of x, and this part comes from the derivative of u of x. So the result is minus e to the power cosine ln x squared. Let me write this as a colored part, I want to use red color because I put u of x in red. Okay, ln x squared times derivative of it. What is the derivative of ln x squared? It goes like 1 over x squared. The derivative of ln function is 1 over whatever you see inside, times the derivative of the insider function. So the final result is this one here. Okay? So we evaluated f, the given function f here, at ln x squared, which is u of x. And then we multiplied it with the derivative of the u function. Any questions now? Always indicate that what theorem you use, you have to indicate the rule that you use. We are applying FTC part 1 here. Okay, if no questions, I want to move on with the next one. Look at the example. Big letter f function is given like that as an integral, and small letter f function is also defined with an integral. We want to find f double prime evaluated at 2. So we should better start taking the derivative step by step. F prime of x, taking the derivative of this definition. Ft dt. And you remember this structure from fundamental theorem of calculus part 1, FTC part 1. This is the simplest form. The result is just what? F of x. This is just x, not depending on, not a function of x, so it is just f of x. We evaluate this function at the x variable like that. Okay, let's take one more derivative. So this is the first derivative of the result. So the first derivative of f is what? F is given like that. So I will derive this given function. Be careful, the variable is given as t here, but I am using the variable x for f. So I will be writing the same definition in terms of x. 1 plus u to the power 4, like this, du. Okay, we are supposed to apply one more fundamental theorem of calculus part 1, where your function is this one. I will be using G notation now. We used already F here. So FTC part 1, how I evaluated it is, this is our, okay, we were calling this as U, but U is already used here. You know, this x-dependent function will be inserted in for the variable of this function here. So it goes like square root of 1 to the power 4 divided by that times u prime. Okay, the function here is x squared, and the function inside will be evaluated at this expression x squared. So whenever I see u, I inserted x squared. What is this now? This is g evaluated at x squared times, you need to multiply this with the function, derivative of this function given here. Okay, so it is in fact just 2x. And this part corresponds to the derivative of whatever function you see here. Okay? So, by applying FTC part 1, the result is just so quick. In a second, we can give the result. But if we wouldn't have this theorem, what we would do? We would first try so hard to evaluate the integral, which is not an elementary one, which takes really a long time. And then after handling the integration, we would take one more derivative, which will take some more time too. Instead of doing all of them, the result is given us in a very quick way, like this, by fundamental theorem of calculus part 1. Okay? And let's find out what is this second derivative function evaluated at 2. I will just insert 2 for x for the result, okay? So it is 1 plus 2 squared to the power 4 divided by 2 squared times 2 times 2. After simplifying here and here, I guess we will obtain square root of 256. Okay, this is another application of fundamental theorem of calculus part 1. Any questions about the solution?
No, teacher.
Everything is clear, right? Okay, let's move on. This is a very nice example. In fact, let me tell you a secret. This was a previous year's final exam question. Okay, let's try this one together. This was a previous year's past exam question. Okay, what we want to find? We want to find g prime 0. That's why we will start taking derivative of this line. You have to be careful on something. We have a product here. This part depends on x, and also the result of this integration obviously depends on x after inserting the boundaries, right? That's why here we have two functions multiplied and they both depend on x. That's why we need to apply for this first multiplication, we need to apply product rule to take the derivative, okay? So it goes like derivative of the first part, which is -1, times the second function. Plus, first stays the same, times the derivative of the second expression here. d over dx, derivative of that integral. g dt. Okay, we can deal with this later. And there is this final expression here, and I take the derivative of it. Okay, then what we have. What about this? How can we take the derivative of the integral? Of course, you should remember FTC part 1 here in the most general form. We have x-dependent functions for both upper and lower boundaries. What we should do then? Let's see. I put a recall about that at the beginning. Where is it? Yeah, here. This time, we are applying FTC in the most general form, where both upper and lower bounds depends on x. We will be doing that. We will evaluate the given function inside at the upper bound, multiply with its derivative, minus evaluated at the lower bound, multiply with its derivative. Let's apply FTC in this form now. G of t should be evaluated at the upper bound, multiply with the derivative of the upper bound. Then g of t should be evaluated at the lower bound, multiply with the derivative of the lower bound. See, this thing is the derivative of this integration this result is given by FTC part 1, okay? Okay, then what we have? We obtained some expression for the first derivative, right? Now, by the way, I haven't inserted 0 yet. This is g prime of x. Now it is time to insert x equals 0. G prime of 0 is, let's insert 0 for all the x's there. Integration from 0 to 0, gt dt plus 1 minus 0 times this whole thing. What do you see there? G of 0 times 0 minus g of 0 plus, now this part, f prime of 0, right? So the integration from 0 to 0 is what? This is nothing. This is just 0 because you are taking integral from 0 to the 0. There is no progress here. Okay, then multiplication with 0 makes this part also 0 too. So what we have as a result here is, I think just these two, right? Just these two left. Minus g of 0 plus f prime of 0. But this is not a real number. We should try to understand what is this or what is this. Let's look at the first line given here. So g of x is given with this expression. We can evaluate g of 0 then. G of 0 is what? Look at its expression and insert 0 for all the x's there. 1 times 0 from 0, gt dt plus f of 0. Again, integration from 0 to 0 is just 0. That's why here we see that g of 0 is in fact the same as f of 0, right? Let's use this information in our last line. Also, there is this information here. It says that f prime of 0 is the same as f of 0. Okay, f prime of 0 is given as f of 0, and I just computed g of 0 as f of 0 too. And you see, then the result is 0 as a real number. Okay? As you can see, it is not that difficult. You should just notice two things here. First, you have to apply product rule to take the integral there like that. And then for this part, you need to apply fundamental theorem of calculus. That's all. The rest is just follows direct computation. Any questions? Okay. If no questions, I want to solve this last example here before the break, okay? Let me handle it before the break and then we can take 10 minutes break. Okay, these are all very conceptual questions about fundamental theorem of calculus part 1 or part 2. Let's see. Okay, there is an integral here and then derivation. This is the exact same structure of fundamental theorem of calculus part 1. So the result is, this is your u of x now. You evaluate your function at the given u of x, and then you need to multiply with the derivative of the given function there, right? So let's write the derivation rule for 2 to the power x. It is itself times ln 2. So this part is the derivation of 2 to the power x, okay? So f of t dt is 0 to 2 to the power x. This is an integral, and then I am taking the derivative of the integral with respect to x. So this can be done by FTC part 1 like that. Okay, next. What about this one? So this one looks so similar to this one, except that the boundaries of the integral are interchanged, and there is one more very crucial difference, that in the second part you are taking derivative with respect to t, not with respect to x, okay? So you should be careful about this. So the question is something like this. You are taking the derivative with respect to t of something. This something is the result of this integral, right? So tell me, the result of this integral depends on which variable? Can you tell me which variable is the result of this integral depends on? Can you see 2 to the power x here? So after taking the integral, you will insert for t first 0, then 2 to the power x, and you will take the difference, right? So the result of the integral depends on which variable?
X.
Exactly, not t, but x. You have to be careful on that because in the boundaries, you are inserting something depending on x. So the result of that integral, we don't know the result, but we know that that result depends on x. Then, look at here. You are trying to take the t derivative of something depending on x. What do you think about this? So this part will just this behaves like a constant with respect to t because it doesn't contain any t inside. If you are taking the derivative of something depending on x with respect to t, it will just behave like a constant. That's why the result of this integral is just what? You can think of that you have just a constant here because it consists of just x, not t. Inside the parentheses, you don't have any t. So the derivative of that expression with respect to t will be just 0. Okay? So that's it. Next, what about this one? Again, the same story. Your function depends on t, and you are trying to take the x derivative of it. So, what is this? What is this derivation then? You are trying to take exactly. You are trying to take x derivative of something that does not contain x, that does not depend on x. Ft just consists of t, not x. So this derivative is 0. That's why you are in fact trying to take the integral of 0, which should be 0 again. Okay? And next here, this is what we cover as FTC part 2. Take the derivative, then integral. FTC part 1 and FTC part 2 are really so similar. The only difference is the ordering. In FTC part 1, you first take the integral, then the derivative. In FTC part 2, you first take the derivative, then the integral. Just the ordering of differentiation and integration are changing in part 1 and part 2. This is one thing. And also, while applying FTC part 1 and part 2, as in these two cases, you should be careful about the variables. Maybe the variables don't match, so that you don't need to apply the rule, you will just have zeros. But here, the variables are matching, right? T. Then you can apply FTC part 2. Derivative, then integration. They will neutralize each other so that we will end up with our function evaluated at these upper-lower bounds, like that. So the result is f of 0 minus f of 2 to the power x, okay? So these are 4 different situations that you have different results. You should be careful about the variables. If they match, you can apply FTC part 1 or part 2. If they don't match, just like here and here, the result can be just 0. Okay? Any questions?
No.
Okay, then let's stop here and take 10 minutes break, okay?